Okay, so in the last video, what we looked at is how why is g the acceleration in free fall. So if you haven't seen the video, check that out before this one. Is my suggestion, unless you already understand that, that's fine, obviously. We're going to look at how we would actually measure g now. So we're going to come back to this method in a moment, but first of all, let's look at the basic idea. If we've got an object falling, then the initial velocity would be zero, so u is equal to 0. Let's say it falls 2 meters, then the displacement would be equal to 2 meters. The final velocity we don't know, and the time we don't know. So to calculate acceleration, we have that. We would need one of these two to calculate the remaining one. The most obvious one seems to be time. And then we'd be able to work out the remaining variable. So if we can measure the amount of time it takes to fall, then we'd be able to work out the acceleration. Let's see if you can pause this video and identify which equation we would want to use. Okay, so here's the Suvat equations right here, and the way to decide what Suvat equation we would need is we've decided we're going to measure the time here, right? So we're going to say, we can tick that because we can say we will have it once we've carried out the experiment. Now, the only variable that isn't included within our calculation is going to be the final velocity. So we're looking for the one equation that doesn't have that in its final velocity. Sorry, in it doesn't have that variable in its equation, and that is this one here. Now I don't know if this is the official second equation, but the point is, it's this one anyway. So if we had this one, we'd be able to work out the acceleration. Let's sub in some of these values. We know that u is going to equal to 0, so we can simplify that down. That would cancel out. So you would have the height, which is s, whatever in our case it was 2 meters. We say h is equal to half at squared. We're going to rearrange it because we want to calculate what a is equal to. So a is going to be equal to 2h over t, 2h over t squared. And that should give us our acceleration. So that's the sort of basics of it, the sort of theory behind this experiment. We do need to understand the methodology. That's what this main thing is really all about. So the methodology is essentially measuring the time accurately, or measuring the height accurately as well, but the much more problematic variable will be the time. If I just get a stopwatch and time how long it takes for something to fall 2 meters, I'm bound to be wildly off because my reactions are just nowhere near good enough to. I mean, it's quite a short time, isn't it? And if you go back to our unit on uncertainty, well, if we try to imagine how much will my reactions, what is my reaction time, then we would say, let's say my reaction time is 0.1 second. Then whatever measurement I'm going to make, it's going to be going to have an uncertainty of 0.1 seconds. Now, how long does it take for something to fall 2 meters? Probably 0.1 seconds, or maybe 0.2 seconds, perhaps, right? Or anyway, less than a second. So I'm going to have a massive error margin, and I could reduce that error margin by taking lots and lots of measurements and then getting an average. But there are better ways of doing it. So there is equipment to do that, and so let's have a look at this equipment. What you do then is you basically you've got this very clever circuit here where the electromagnet which is holding the steel ball up in the air. So you can see that when the switch is opened, the electromagnet would release the ball, and simultaneously a timer would start. As soon as the electromagnet falls through this trapdoor, sorry, as soon as the steel ball falls to this trapdoor, it will break the circuit and the timer will stop. So the timer starts when you press the switch and stops when it falls through that trapdoor. So now it's going to be a lot more precise. The timer is going to be a lot more precise than the reactions of a human. So as you can see, we've got down here the equation that I chose. They've used slightly different symbols because obviously I said A, and as they've said here, A is G. So rearranging it, we said S, which I wrote as H, is equal to half gt squared. And rearranging that, G would be equal to 2s over t squared. So we take a bunch of different measurements. Here you can see that they've got a variable. They've changed the distance, right? And then they've measured the time on each case. Now they've plotted time squared, and the reason, and this is it's a new skill specific to A level. It doesn't come up in GCSE really, or they've just started to bring it in. If I plotted distance against time, we can see from the equation that it would be, you get a square relationship. So in order to test our theory properly, we're going to plot it against t squared, and we will get a linear relationship. So we'll get a straight line. In other words, because s is equal to half gt squared, and we know that half is obviously a constant, g will be a constant, then we're going to say that s is directly proportional to t squared, right? When I double the displacement or the height, I would double t squared, but I wouldn't double t. I would just double t squared. So if I plot it against t squared, I'm going to get a linear relationship like this from the origin. And when I have that, that means I can measure the gradient and I can see the intercept. Now the intercept should be 0. Otherwise, I've done something wrong with my experiment. And then we can measure the gradient. So what would the gradient be? Well, the gradient would be half g, wouldn't it? Okay, so remember the gradient is equal to the change in y, which is distance in this case, over the change in x, which is time, or time squared, I should say. So that's going to be the height, and we could say divided by t squared. And as you can see, that's going to be equal to half g. So in other words, double the gradient will be equal to the value for g. Okay, so 4.89 it says there. Well, let's see, what does 4.89 times 2 give us? Okay, so according to when we multiply that, we get 9.78. So very close to 9.81. You could go on to work out the error, the percentage error of that, the absolute error and the percentage error of that. We know that we can look up on the internet what is the official the official accepted value for g, and how close are we, and so on. And you can see they've got error boundaries here. So how do they get these error boundaries? Well, I'm not sure if it says here, but basically it's down to the uncertainty within the measurement, within the things that they're measured. So okay, let's have a look at, yes, of course. So why do they get gradually larger? They get gradually larger because there's going to be a certain fraction of an error within the time, and as the time is increasing, then the error is going to increase by that same amount. I guess that's what that will be. I don't think it explains it very clearly, but that's my guess. So let's have a little read of some of these. In fact, let's now just go to the question. So I'll save that video now.